If you have a geometry problem where you need to find the area of a regular polygon, follow these steps. First, divide your polygon into triangles. Since it's regular, all of the sides are the same, all of the angles are the same. You divide it into triangles, all of those triangles will be congruent. For instance, if you have a hexagon, it has to be a regular hexagon, so all the angles inside are the same. If you divide that into triangles, there will be 6 congruent triangles. Same thing if you had an octagon, it'd be 8. If you had a heptagon, it'd be 7 equivalent triangles. Next, you want to use trig to determine the height and the base of one of those triangles. And if it's a regular shape, all of those triangles are congruent. So it's only the base and the height of all of them. When I say trig, it's generally going to be tangent, because tangent of this angle would be opposite over adjacent, which opposite includes half of the base, adjacent includes the height. Specifically using tangent. And then once you have the height and the base, find the area of one triangle. Again, they're all going to be congruent triangles. So if you know the area of one, then you know the area of each of them. And then you multiply that by the number of triangles, which is also the number of sides in the polygon. Okay, so if you follow those steps, dividing your polygon into triangles, finding the base and the height using trig, finding the area of one triangle using your base and your height, 1/2 times base times height, or base height over 2, and then multiply the area of the triangles by the number of triangles. Then you'll be able to find the area of any regular polygon. Again, it has to be regular for this to work. If it's irregular, then the triangles won't be the same size. I'll go through 4 examples now how to implement this in greater detail. In this question, we're finding what is the area of a regular pentagon with sides of length 5 centimeter. So regular means that all the sides are the same as each other, all the angles are the same as each other. In this case, that's important because if we know the lengths are 5, they're all going to be 5. The only way that we can find the area, given only the side length, is if the angles are all the same, because that means we can divide it into 5 equal sized triangles, going from each vertex to the middle, like that. And since all of the angles are the same, then you just divide them in half. There are a couple ways that we can find the angles of these triangles. One of them would be to find each interior angle. So you can use the formula, the total of the interior angles is equal to 180 times the number of sides minus 2. In this case, that'd be 180 times 5 minus 2, which gives us 180 times 3, so 540. And then if you divide 540 by 5, you'd get what each one is, which is 108. So that's one way you could do it. You could use exterior angles. We know that the total of the exterior angles is 360 degrees. So if you divide that by 5, you would get that each exterior angle equals 72 degrees. And then you could use that to find the interior angles by doing 180 minus 72. The exterior and interior angles are supplementary. So those are a couple ways you could do it. But I think that the easiest way to find the angles of these triangles would be to find this top angle, interior angle, the one that's coming from the center. And we just know that all of these angles add up to a circle, right? They make 360 degrees, and there are 5 of them. They're equal parts. So you could just divide 360 by 5 and find this angle, which we had already done up here. Gives us 72 degrees. So each of these would be 72 degrees. And now we can move on with finding the area of this pentagon. So we know to find the area of the pentagon, we want to find the area of one of these triangles. And since they're all congruent to each other, we would just multiply that by 5 because there are 5 of these congruent triangles. So I'm going to redraw that triangle right here. We know that the top angle is 72 degrees. The 2 bottom angles are the same as each other. They're just dividing those 108 into halves. And now we can drop down an altitude. So we're making a height. It has to meet it at 90 degrees. It's dividing this triangle into 2 halves, which means that 72 will get split in half. Half of 72 is 36. So we get 36 degrees here and 36 degrees here. Now, using the fact that the side lengths are all 5, we can figure out the base of this right triangle, which would just be half of 5. So 5 halves, so you could write it as 2.5. And we can use that to find what this height is. Right? We need that height so we can find the area of the triangle, because the area of a triangle, they're 1/2 base height or base height over 2. Those are the same thing. So once we find the area of the triangle, we can use that to find the area of the pentagon, because the area of the pentagon is equal to 5 times the area of the triangle. So right now, we know we need the area of the triangle. To get the area of the triangle, we need the base, which we already have. The base is 5. What we need is this height. We're just solving for the height. And to solve for that height, we can use some of our basic trig functions, or in this case, we only need to use one of them. So we have that this angle here is 36 degrees. That angle is across from or opposite this base, 2.5, and it's adjacent to the height, right? The hypotenuse would be this length over here, which we don't need in this case. it won't help us find the area of the triangle. So we can say which of our trig functions uses opposite and adjacent. That would be tangent, right? Tangent of theta is equal to opposite over adjacent. Use SOHCAHTOA, that's the TOA, TOA. So in this case, tangent of 36 degrees, make sure your calculator is in degree mode when you type that in, would be equal to the opposite, which is in this case 2.5, over the height, which is what we're solving for. All right, so now we have an equation that says one variable, so we can solve for it. To get that h alone, we're going to multiply both sides by h, which would give us h tangent of 36 degrees is equal to 2.5, right? The h's cancel out up here. And now we want to get the h alone, so we get rid of the times tan of 36 by dividing both sides by tan of 36 degrees. Again, that cancels the tan over here. We're left with that the height is equal to 2.5 divided by tangent of 36 degrees. Now we could type that into a calculator and get a rounded value for it right now, but we know our answer is not the height. So we're going to need to plug this value in to our other equations. So first we'll plug it into this equation, and we'll plug that value into the top equation. So I'll just leave it in terms of tangent right now. When I put it in, you could also use the store button on your calculator or just round it a lot further than what you're going to ultimately round it by. So our area of the triangle will be equal to the base of the triangle. And again, that's not just this 2.5 down here, that's this entire base, which we said was 5. So our area is equal to 5 times the height we said is 2.5 divided by tan of 36 degrees. Again, you could have calculated a value there and gotten a really long decimal or a stored value in your calculator. And then we're going to divide that by 2, right? Because it's 1/2 base times height. When you plug that in, you'll get a decimal, and then you can put this value in to 5 times the area of the triangle. So the area of the pentagon would be equal to 5 times the area of the triangle. So if I open up Desmos here, I'll have 5 times 2.5 divided by tangent of 36 degrees, make sure it's in degree mode, and divide that all by 2, which gives me 8.602387, and I'd have to multiply that by 5 because that would be my area of the triangle. Area of the entire pentagon is equal to 5 times that 8.6024, which gives me 43.0119. If they ask us to round that to the nearest hundredth, we'd say that it's 43.01, and our units were centimeters. So since it's area, it's going to be centimeters squared. So that's a lot of steps, but ultimately the main thing we're keeping in mind is we're dividing that regular polygon into triangles, and the number of triangles is equal to the number of sides. Then with that triangle, we have to find the height and the base, so we can calculate the area of the triangle. Once you have the area of the triangle, then you can use that to find the area of the entire shape. All right, for this next one, we're finding the area of a regular hexagon with perimeter of 60 inches. So this time they gave us the perimeter, which means to solve for the side lengths, we have to divide by the number of sides, right? The perimeter of a regular shape would just be the length of one side times the number of sides. So in this case, divide by 6, we get that each side is 10 inches. And again, if we want to find the area, we're just going to divide that into 6 equally sized triangles. Now what's nice with a hexagon is that for a hexagon, all of the angles add up to 720. So if it's regular, all of the internal angles are 120. So if you divide that in half, you get that each angle inside is 60 degrees, including these angles up top, which you could also prove by doing 360 degrees divided by 6. 360 divided by 6 is also 60. So what that means is for a regular hexagon, you're actually not just made up of 6 triangles, you're made up of 6 equilateral triangles. So all of the sides and all of the angles are the same. Meaning that if these sides of the hexagon are 10, then these hypotenuses of the right triangles that we're going to draw are also going to be 10. This will save us some time because when we're trying to find the area of the triangle, even if you don't know the formula for the area of an equilateral triangle, you can break it up like this, and you'll have these 60-degree angles at the base and at the top. This top 60-degree angle gets cut into 2 equal-sized 30-degree angles. So what we actually end up with is a 30, 60, 90 right triangle. And the 10 here will be cut in half. So we have 5 over there and 5 over here. With a 30, 60, 90, the sides will be in the ratio of x to x root 3 to 2x, with the biggest side opposite the 90 degree angle, the x root 3 opposite the 60 degree, and the x opposite the 30 degree. So that means that in this case our x is 5, 2x is 10, and the height, x root 3, will be 5 times the square root of 3. So in this case we don't even need to use trig, just because for a hexagon, or regular hexagon, they're equilateral triangles. So we already know the height is 5 root 3. So if you need to find the area of one of these triangles, you'd again use base height over 2, or 1/2 times base times height. In this case, our base is 10, so we do 1/2 times 10 times 5 root 3. Will give us that the area of the triangle is equal to 1/2 times 10 is 5, 5 times 5 is 25 root 3. So that's the area of one triangle. We're finding the area of the hexagon, which is made up of 6 of these equal-sized triangles. So we'd say the area of the hexagon equals 6 times area of triangle, which means it's 6 times 25 root 3. So the area of this hexagon is equal to, well, we'd say 4 times 25 is 100, then 2 more 25s gives us 150 root 3. Our units are inches squared. And if you wanted to round that to the nearest hundredth, for instance, you would 150 times the square root of 3 is 259.807, which is about equal to 259.81 square inches. That would be our answer there. So again, that one was faster just because we skipped the step of the SOHCAHTOA using the special right triangle, the 30, 60, 90. That will only work for hexagons. So for this octagon, they give us that the apothem has a length of 8 millimeters, and it's also regular, so all the sides will be the same. We don't yet know what they are, but let's again do our first step and just divide that up into, in this case, it will be 8 equally sized triangles by connecting all of the vertices to the center. I know I didn't draw it perfectly there, but now we know the apothem, which is the distance from the center to the midpoint of each of the sides, is going to be 8. Here, essentially that's the height of those triangles, or it is the height of those triangles that we're doing. So in this case, we still need to find the angle up here, and we'd say, all right, well, the entire center, if you do a circle there, it would add up to 360 degrees. So if we want to find each angle, we divide that 360 into 8 equal slices. So 360 divided by 8 divided by 4 would give us 90, divided by 2 is 45. So each of these angles up top is 45 degrees. So if we redraw our triangle, we have 45 degrees up here, and the height has a length of 8. We want to divide that into a right triangle. We do half of 45, which would be 22.5. 22.5 over here, 22.5 over here. And now we can use SOHCAHTOA. So in this case, we'll use tangent because we need to find this base down here, which ultimately we want to find the entire base. So we're going to have to multiply it by 2. Well, this base, then what we're solving for is base over 2. So that's opposite the 22.5. The 8 is adjacent. Again, we're using opposite and adjacent, so we want to use tangent as our trig function. We'd say tangent of 22.5 degrees equal to this base over 2, right, this thing right here, which is the opposite, divided by this adjacent, which is 8. So now to get the base over 2 alone, you'd multiply both sides by 8. Cancels here, and that gives us that base over 2 is equal to 8 tangent of 22.5 degrees. If we want to get just the base, then we would multiply both sides by 2. And we get that the base of the triangle, again, this big triangle, is equal to, well, 2 times 8 gives us 16, so it's 16 times the tangent of 22.5 degrees. All right, so that gives us the base of the triangle. To find the area of the octagon, we need to do 8 times the area of each of those triangles. The area of each of those triangles is the base, the thing we just solved for, times the height. The height was the apothem in this case, so that's 8, divided by 2. So we said that's 16 tan 22.5 degrees times the apothem, so times 8, all divided by 2, and that gives us the area of the triangle is equal to, in this case, 8 times 8, so 64 tan 22.5. And we're going to be multiplying that entire thing by 8. If we want to find what the area of the triangle is first, 64 times tangent of 22.5, it's in degree mode. That gives us 26.50966, and we want to multiply that by 8 to get the area of the octagon, which is about equal to, make sure that your times 8 is outside of the parentheses there, so it's not part of the tangent, 212.0773. For rounding that to the nearest hundredth, that would give us 212.08. Our unit here is millimeters, so if we're doing the area, it's millimeters squared. 212.08 millimeters squared. So even though this one didn't give us the side length, right? The previous ones gave us either the side length or the perimeter that you can use to find the side length. It gave us this other thing, the apothem, but the principle is the same. We're dividing the shape, this polygon, into equal sized triangles. Then with those triangles, we have to find the base and the height. If they give you the apothem, they give you the height of the triangle. If they give you the side length, then they give you the base. So you use trig to find whatever you don't have, either the base or the height. Then from there, you can find the area of the triangle, and then multiply that area of the triangle by the number of triangles. So in this case, there were 8 triangles, so we multiplied the area of the triangle by 8, and that gives you the area of the entire polygon. Okay, so we'll do one more example. This one is a decagon. And this one, they gave us that the perimeter is 85 meters. So a decagon has 10 sides, and you can count that to be sure. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got a decagon here. And if the perimeter is 85 and it's a regular decagon, that means each side is the same. So we can divide 85 by 10, which gives us 8.5. So each side is 8.5. So we can say, maybe that makes it a little bit trickier that it's not an integer, but the math will stay the same. And since we're using a calculator, it doesn't really complicate it very much. Now, we want to divide that into, as usual, a bunch of triangles. In this case, there are 10 triangles. Now, you can say I didn't draw it perfectly there, but 10, it should be equal-sized triangles. And this one, I'm definitely just going to use the angle in the middle, because we have 360 degrees for that circle. If you divide it into 10 equal-sized slices, that gives you 360 divided by 10, which is 36 degrees. So we have 36 degrees. If we redraw that triangle, or any of these triangles, it would be 36 degrees up here. And we said that the base down here is 8.5. So if we drop an altitude down, it cuts that 8.5 in half. Half of 8.5 would give us 4.25. And it cuts that 36 degrees in half. Half of 36 would be 18 degrees. All right, so we have a right triangle. We need to find this height here, which is adjacent to the 18 degrees. So again, we're using tangent. Since we're never finding this, basically the hypotenuse of the right triangle here, we're only going to be using tangent, because we either have opposite and want adjacent, or we have adjacent and want opposite. So we'd say that the tangent of 18 degrees is equal to, in this case, opposite of 18 is 4.25, and adjacent is the height, so the thing that we're solving for. Right? The thing we need to find the area of the triangle is the base and the height. They gave us the base, 8.5. We're finding the height. So this one is very similar to the pentagon, where the height is on the bottom. So to get the height alone, just multiply both sides by height, and then you want to divide both sides by tangent of 18. So I'm just going to do them one step at a time. So h times tan 18 equals 4.25. That should be, the degree should be inside the parentheses. So divide both sides by tan of 18. Make sure you're in degree mode. The tangent of 18 degrees cancels out over here. That leaves you with the height is equal to 4.25 divided by the tangent of 18 degrees. Now I'm going to show I usually, again, will either store this value in my calculator or keep it in this form until the end. But for people who like to use the calculator first, you could go 4.25 divided by the tangent of 18 degrees. We're in degree mode. So it gave me 13.0801550003. For this problem, they might have asked you to round your answer to the nearest hundredth or tenth. But since we're not at the final answer stage, I'm going to write this entire number, or at least a few digits beyond what I need, so that I don't round too early and then end up, rounding up or rounding down when I shouldn't have. 0.3. All right, so I'm leaving all of those digits just so that, again, I don't round too early. That's my height. Now if I want to find the area of the triangle, it would be the base, which was again 8.5, times the height, what we just solved for, divided by 2. So I could type that in as 8.5 from here times 13.080155. And doing this many digits might be overkill, but again, if I just rounded it right to 0.8 right there, it might end up giving me the wrong answer by 100th or 200ths. Divide that by 2. So if I type that into my calc, 13.08015503 times 8.5 divided by 2. Doesn't matter if the whole thing is divided by 2 or just that, because it's basically you're multiplying the entire thing by 1/2 anyway. That gives me 55.5906588. All right, so again, I'm still not going to round because I need to multiply that by the number of sides. We had a decagon, so we could say the area of the decagon is equal to 10 times the area of the triangle. So 10 times 55.590658888. That's essentially just going to move the decimal place over 1, or it is going to do that. So that means our area is approximately equal to 555.9065888. If we round that to the nearest hundredth, then we need to round this 6 up. So it would be 555.91, and our units in this case were meters. So for the area, it will be meters squared. Okay. So for all of these, you can see there's a lot of work involved because you do need to do a number of different steps. First, dividing that shape into equal-sized triangles. Then to find the area of those triangles, you need to use trig to find a missing side, either the height or the base. In general, it's going to be tangent. Right? I would still check it each time to make sure you're doing opposite and adjacent, set it up correctly, take your time. Then once you've got either the missing height or missing base, you can plug that into your area of the triangle, 1/2 times base height over 2. And then once you have the area of the triangle, just multiply it by the number of triangles. Again, this trick will only work if it's a regular shape. You can see all of these were regular octagon, regular decagon, regular hexagon, regular pentagon. If it's an irregular shape or even a concave shape, then this strategy won't work because the triangles won't be the same size. All right, well, comment below if you have any questions on how to do this, but this was, it was a pretty exhaustive approach to getting these answers. Make sure that you are rounding correctly. Again, I like to save my numbers in form of tangent or in form of radical until the very end. You can also use the store button, or just like I did in this last problem, round way beyond what you need until the very end and then round to the point that you need.